Look at the window nearest to you, right now. That pane of glass is already doing two things, and nobody is harvesting either one. During the day, it absorbs wavelengths of sunlight invisible to your eyes. At night, it radiates heat outward toward a sky so cold it sits just a few degrees above absolute zero. Both of those are energy flows. Both are happening continuously. Both are currently going to waste. A standard home loses between 25 and 30% of its heating and cooling energy straight through the glass it already paid for. Every hour, every season, no interruption. Now imagine a transparent panel placed exactly where any window goes that generates electricity from sunlight during the day and from the temperature difference between your warm interior and the cold night sky after dark. No moving parts, no compressor, no opaque surface blocking your view, no battery required for the cooling function, no roof modification, just a pane of glass doing what glass has always done. Except this time, the physics is captured instead of wasted. What exactly is this panel? How does it pull electricity out of darkness? And why is no version of it sitting in any hardware store? The answer to that last question is not a technical failure. It is something more uncomfortable than that. The window as a passive energy surface is not a new concept. It just had a different name for most of human history. Roman and Byzantine builders already understood that south-facing openings captured winter heat and reduced the fuel needed to warm interior spaces. This was not aesthetic preference. Mica sheets and thin slabs of alabaster served as early translucent glazing in Roman bathhouses, trapping solar warmth inside stone walls without blocking light. The pane of glass is not a modern invention. Only its industrial scale is. Medieval builders in Europe and across the Islamic world oriented their rooms, courtyards, and window apertures not according to street plans or symmetry, but according to the seasonal angle of the sun. Thick stone walls with narrow south-facing openings admitted winter light and blocked summer radiation. The geometry itself was the climate system. No furnace, no thermostat, no electricity bill. The building was doing physics, and the builders understood exactly why. The third layer of this tradition is stranger and more impressive. Persian and northern Indian engineers understood that objects facing an open night sky do not just lose heat to cool air. They lose heat directly to the cold of space, through a process that operates even when ambient air temperatures are mild. Shallow pools, domed rooftops, and specially shaped cisterns in Iran exploited this effect to produce ice on winter nights, even when the surrounding air never dropped below freezing. The sky was not just a view. It was a cold reservoir, and these builders knew how to aim a surface at it deliberately. These were not accidents. They were engineered responses to understood physical phenomena. Solar gain, thermal mass, the emissivity of materials, and the thermal sink of an open atmosphere. The window as a passive energy engine is not a discovery from a 2024 laboratory. It is a forgotten infrastructure principle, and now it is being rediscovered with new materials. At MIT and Stanford, research groups working on transparent photovoltaics and radiative cooling films arrived at their projects separately. The transparent solar team was solving one problem: how to make a solar cell that does not block visible light. The radiative cooling team was solving another: how to make a surface that cools passively by emitting heat to the sky. The convergence of those two problems into a single surface is where the modern proof case begins. The daytime function works like this. Standard silicon solar panels are opaque because they absorb across the full visible spectrum. Transparent photovoltaics use organic dyes or quantum dot materials that absorb only near-infrared and ultraviolet wavelengths, bands invisible to human eyes, while allowing visible light to pass through unchanged. The absorbed photons excite electrons, and that electrical current is harvested at the panel's edge through thin conductive channels embedded in the frame. The window still looks like a window. The glass is doing work the eye cannot see. Some designs add another layer of clever. A fluorescent film inside the panel re-emits absorbed energy at a different wavelength and re-emits it into waveguides toward the frame edges, where conventional solar cells convert it to current. The glass itself becomes a light pipe. The frame does the generating, and the pane does the collecting. This is why the surface stays transparent. The energy is steered sideways, not converted at the face. The night function uses different physics entirely. Every warm surface radiates heat as infrared light. This is not technology, it is thermodynamics. Earth's atmosphere happens to be transparent to infrared in the 8 to 13 micron range, meaning a surface engineered to emit strongly in that band loses heat directly to the 3 Kelvin cold of outer space, with almost no atmospheric absorption blocking the path. A correctly designed outer coating can drop the window's outer surface temperature 5 to 10 degrees Celsius below ambient air on a clear night, without any energy input. This is the same mechanism that forms frost on car roofs when air temperatures are still above freezing. The sky is cold. Materials that face it correctly get cold too. Place a thin thermoelectric element between that radiatively cooled outer face and the warmer interior surface, and you have a generator. No refrigerant, no pump, no moving part. Just a material that reads a temperature gradient and outputs voltage. At night, the outer face is cold, the inner face holds room warmth, and the panel converts that difference into current continuously. The real trick is that both functions share the same surface and the same installation footprint. During peak solar hours, transparent harvesting runs. As the sky clears at night, thermoelectric generation begins. The panel also blocks a portion of solar heat from entering the room during summer, reducing the cooling load the building carries. The benefit is not single, it stacks. Early MIT lab results on transparent luminescent solar concentrators showed power conversion efficiencies between 1 and 5% for fully transparent versions, rising toward 10% in lightly tinted designs. Small numbers individually, large numbers when applied across the entire window area of a building. For a home with 20 square meters of south and west-facing glass, these panels at current efficiency levels could offset 10 to 20% of base electrical load before the cooling load reduction is even counted. The standard double-pane window on a south-facing wall contributes net zero to building energy over a year. It loses in winter. It overheats in summer. This panel makes the same surface net positive. There is a sensory dimension that statistics do not capture. No humming compressor is added to the window assembly. No opaque surface cuts the view or the daylight. In summer, the interior simply feels slightly cooler. The panel absorbed what would otherwise have entered the room as radiant heat. At night, the outer glass quietly emits to the sky while the room holds temperature longer without the heating running. The building becomes less dependent on mechanical systems doing constant work. It depends more on materials doing physics. That is a different relationship with a building than most people living in sealed, ventilated, compressor-dependent homes have ever experienced. So why is this not standard? The honest answer starts with a real limitation. Current fully transparent solar efficiency is dramatically lower than opaque silicon panels. A rooftop silicon panel converts 20 to 23% of incoming solar energy. A transparent panel converts 1 to 5%. It is not yet competitive per dollar installed against standard rooftop solar, and the nighttime thermoelectric output is measured in milliwatts per square meter, not watts. Cloud cover suppresses both functions simultaneously. In humid climates, the radiative cooling effect weakens. The manufacturing process for quantum dot and organic dye layers remains technically demanding and expensive at scale. These limitations are real and they matter. But they do not fully explain why the principle sits at the edge of commercial availability, rather than at the center of every new building specification. Glass manufacturers profit from selling certified, sealed units with documented thermal resistance values. A transparent photovoltaic coating disrupts that product category without fitting neatly into any current building code performance standard. Building codes classify windows by heat loss and solar gain coefficients, not by generation potential. There is no certification pathway that gives a contractor or a developer a straightforward compliance route. Energy utilities have little incentive to accelerate a technology that reduces grid dependence per window. Developers building multi-unit housing choose window specifications that minimize upfront cost because tenants pay electricity bills, not developers. The generation value of a premium panel simply does not appear in the developer's return calculation. Architects and contractors are trained around familiar product categories. A window that generates electricity requires new installation knowledge, new warranty structures, new insurance categories. The supply chain for conventional aluminum frame glass units is deeply entrenched, and it does not easily absorb a product that requires different fabrication, different edge treatments, and different quality verification. The technology is too passive, too durable, and too distributed to anchor a recurring revenue model. That is not a conspiracy. It is a structural problem. Markets reward what can be standardized, sold, serviced, replaced, and billed. A surface that quietly generates electricity for decades with no moving parts and no service contract does not fit that model well. The principle can still be reclaimed. Commercially available transparent solar film exists through sustainable architecture suppliers and specialty glazing manufacturers at pilot scale. South and west-facing glass maximizes the daytime function. Unobstructed sky view on the outer face maximizes the nighttime function. Orientation is not optional, it is the design. Do not assume that any low emissivity coating is equivalent. Standard low emissivity glass reduces emissivity to retain indoor heat, which is the opposite of what the radiative outer layer needs. A tinted or reflective coating is a different thing entirely. Passive house architects already optimize glazing orientation and solar exposure. Transparent solar panels are a direct upgrade applied to that existing discipline. Thermoelectric kits are available for workshop prototyping. Research groups are publishing open data on radiative cooling surface fabrication. The physics is accessible, and small-scale implementation is already underway in off-grid and sustainable building communities. The window is not an inert object. It never was. Roman builders shaped stone openings around the sun's angle. Persian engineers aimed rooftop surfaces at the sky to manufacture ice. Medieval craftspeople encoded seasonal physics into the thickness and placement of walls. All of them understood that the surface between inside and outside was the most powerful thermal instrument in a building, and they treated it accordingly. The principle was not abandoned because it stopped working. It was sidelined because glass sold by the pane, billed by the unit, and maintained by the glazier generates a supply chain. A window that generates electricity and pays for itself does not. Every building material holds latent function that modern construction categories were not designed to capture. This is one example. There are others. If a window can cool a building by emitting heat to the sky above it, consider what a roof engineered entirely around that principle could do, not to a single house, but to an entire city running 10 degrees hotter than the land around it. That question, and the answer already waiting inside material science, is where this story continues.